go. Okay. Not so sure if this is going to be a successful one, but let's try again. So I'm going to now spend like 10 more minutes here and we're gonna move on. And maybe it's still not clear for you. It's perfectly fine. I know that today I'm not very helpful on that. We can come back. So the things, the other way to explain it that I wanted to try might work, might not work. You'll see. I'm not saying that it's the final and we're not talking about it at all anymore. We will talk about it again. Okay. So, since, well, here what I wanted to say is, first of all, ask you this question. So, if I have 4 cups and 2 cookies, how many bundles will I be able to create? Type. One. Okay. We all agree on that. That's perfect. Because even though I have 4 cups of coffee, I'm not gonna drink them all because per each cup I need 2 cookies and I only have 2 cookies. Perfect. So this is pretty much why this point will bring us, like here, I'm saying 4. This point will bring us back to the initial where we started. So the goal of the utility function is to always choose the points that are here on the green line. That will be also the number of bundles that we're choosing. Okay, so try to think of it this way. So what utility function does is bringing us to, well, the number of bundles that we're able to create. And since, why is it 2x? That's the last thing. Why is it 2x equaling y? Well, I was saying that I need 1 cup of coffee and 2 cookies. So 1 cup of coffee, 2 times 1 equals 2 cookies. So this might not make sense economically, but it makes perfect sense mathematically. Because I'm saying, okay, the first bundle has to work like that. So I have 2 cookies and I have to have 1 cup of coffee for it to be equal, right? Yeah, don't want to give another example. Again, so this equation does not hold if I put it the other way around. If I put x is equal to y, then I'm gonna put 1 cup of coffee and here on the right I end up with 4, and this is not equaling each other. So that's why it is 2x equals y or y equals 2x. So I think this is the crucial for you to understand right now, that this is going to be the way to represent it. If you still don't understand, we'll get back to it. It's just that I realized that we spent so much time. Okay, cool. I have 2 classes from Karim. It gives me hope. Okay, so that's it. I'm going to work with this word a little bit more before sending it to you. So it's going to become pretty with more steps. For now, you have to understand that this is the case for this framework, and the utility function will take a form of minimum. And we'll see again with, I think offline will be better, and don't worry at all because you see it in your micro again and it will be explained to you again. Before even I start reviewing presentations, so as you can see here, what we have first is the outline, and we start straight with warm-up exercises. But I want to first check what is the purpose of derivative, what derivative is. So in general, derivative of a function shows a rate of change of this function. So this is something that you should recall maybe from before, or if you don't know what derivative is, that's the main explanation that we will use, the main sense of derivative. So it's a rate of change of the given function. So if, for example, we increase our argument by 1, by how much will our function increase? So when we use derivatives in economics, we usually want to know by how much will our cost increase if we increase a production by 1 unit. So this is where we take a marginal cost, and marginal cost is calculated with the help of derivative. Okay, great. So let's take an example first of a linear function. So we're just going to draw a line like that. And let's say that here this is 1, and on the y-axis I'm gonna have 2. Just I know that the scale is not correct, but well, you see what I mean. So here we're gonna have 2, and here I'm gonna have 1. It's an example of a function. Well, it's the same as from the minimum, but well. Okay, cool. Perfect. So I see that every time x increases by 1, y increases by 2. Because this is the function y equals 2x, right? And then every 1x we add 2 y's. Like from the coffee and cookies example. So the derivative, I said that this function is y equals 2x, and the derivative of y with respect to x is equal to what here? Now you have to tell me because you were supposed to revise it. It's equal to 2. Perfect. So, sorry. Okay, now if we have a function that looks like 2x, its derivative is equal to 2. And we can first of all see it straight from the graph, because by every x we add 2 y's, or we can recall the formulas that constant times x, the derivative will be equal to x. Okay, perfect. Well, that works really sweet in case we have linear functions. Here we see the derivative directly from the graph. That's amazing. So we can also say that derivative measures the steepness of the graph, so its slope. And in here we have constant slope. Perfect. But what if our function is not a line? What if our function, for example, is a parabola, right? So first of all, if I apply the definition of rate of change, well, I understand that it changes, well, not everywhere the same. For example, in the beginning, the way you recall parabola, the quadratic function, the square function, it increases not that fast, and then it starts increasing a little faster. Wait a second. This Zoom stuff. Wait, how can I do it? like that. Okay, cool. I broke this system. Okay, cool. So let's put this. It's not a parabola. Well, it is. Make it more visible, like that, or even like that. Perfect. So now we have this kind of function. You see that in the beginning it increases slower and then it starts increasing faster. So for this kind of function, makes sense that derivative is going to be a function. So the derivative will change and will take different values when x takes different values. So this point is, at this point, the derivative is one thing, and at this point the derivative will be another thing. Okay, great, perfect. So we understand that just by looking at the function, and we will have different slopes in every point. So we'll have to deal with derivative in general and derivative at a point. So oh, sorry. You also should remember something that tells you that derivative is the slope of a tangent to a graph. So since in case of a function that is nonlinear, derivatives are different for each point, we can find an approximation saying that, well, for example, for the first point, derivative will be the slope of this curve. This curve that is green curve line is a tangent to this graph at this point. So the derivative for this point will be the slope. And we can say that that will be the rate of its change. So in economics, as I already said, the most common example is marginal everything. So marginal cost, marginal utility. What is marginal utility? It is by how much the utility increases if I add one more unit of my good. And it certainly depends on where I am, because if I have zero of this good, maybe the first unit will increase my utility by so much that, well, the derivative will be great. But then the more of the good I have, the less utility each additional item brings me. So that's perfect example of how derivative is changing along the line. So you should think of anything. With the costs, you also can understand that it works like that. With the marginal product of labor, I'm sure you've seen this example where they tell you, well, now imagine we have 3 workers, they're okay, we have 4 workers, well, the productivity increases because they help each other, but at a certain point they start bothering each other, there is not enough space for everyone, and we end up with smaller additional product by new worker. Okay, perfect. So that's it for the graph that I wanted to show you. It doesn't make much sense to even save it and send it to you. It was just to show you different cases. One constant derivative and another is changing derivative. And constant derivative we only have when we have linear function. Okay, cool. So now I need wait a second. I need this and wait, stop. Closing our Word, and let's just open the notebook again. I'm going to download the previous notes of the notebook and start new notebook. So I'm erasing the first part. And okay, perfect. So now we're back to our favorite framework of two windows. Okay. Here you go. Please put pluses if on the left you see warm-up exercises and on the right you see my online thing of matcha. Okay, cool. Thank you very much. Thank you. Okay, great. So for the warm-up exercises, I'm going to give you just 5 minutes. That's gonna be enough. To calculate the first derivative of the following functions. For now, you shouldn't worry very much what's first derivative mean. It just means calculate the derivative following these main formulas. Okay? So here are the exercises. Here I'm going to write the solutions. And here you go. You have your 5 minutes. It's okay, so let's just check it real quick. So as I told you, not spending much time here, and just to check. Look, this notation is one of the notations that we use for derivative. So by the end of this presentation, you'll see that this is has to be first derivative, and it has to be, in case of one variable, both partial and total. But for now, this is the notation that I'm going to use, because for sure it's correct for this case. And then we'll see more notations, and in the end we'll do a bit of catch up. So what is the difference between them? Okay, so for the first one, the answer is 0, because there is no x that is changing. And if you imagine the graph of this thing, it's a horizontal line. So you think of it with the logic of derivative. So by how much y changes when we increase x by 1, by 0. Y never changes, because the way it is just a horizontal line fixed at the level of a. Yes, exactly, perfect. So one assuming we take derivative with respect to a, yes, but we're assuming that we're taking derivative with respect to x, and I agree that I didn't mention what is the variable. So I was supposed to say calculate the first derivative with respect to x of the following functions. So now this is clear when I precise. Now, the second one will be 2x plus 1. The third one will be minus 2. So here I'm going back to this formula. I know this. So x to whichever power is supposed to be power times x to the power of the initial minus 1. Perfect. So here what are we going to do? We're going to write it like that. 2 to the power of, it was minus 2, right? And then we have to subtract again 1. So I forgot x, sorry. Minus 2x to the power of minus 2 minus 1. So this is minus 2x to the power of minus 3. Or I can write it also as a fraction, because we know that negative exponents, that's what they do. That will be x cubed. That will be like that. Okay? So all three of these notations are accepted. You can keep it like that. You can do it a fraction. Doesn't matter. Okay, so for the next one, where we had x cubed plus 1 over x. So x cubed, that's giving us 3x squared, because 3 minus 1 will be 2, plus, okay, here as you saw, there is nothing like a main formula for 1 over x. And how do we deal with the derivative here? So the way I suggest you to think of the fraction is the following. Before I'm gonna write it, so y of x, I'm gonna rewrite it. So I'm gonna say that it's x to the power of 3 plus x to the power of minus 1. This is absolutely correct because it is the same as saying x cubed plus the fraction. And now it's becoming easier. Why? Because you know how to take a derivative if we have x to the power of something. This formula, the most used. So we're gonna have here minus 1 times x to the power of minus 1 minus 1, right? Because we just do the formula. We follow it. We were supposed to subtract 1. We're subtracting 1. Okay, that's going to be 3x squared minus x to the power of minus 2. And if we want to write it as a fraction, we also can. If no, minus 2 is a perfect exponent to keep. Then, for the square root, do I have a square root? I don't have a square root, even though these two things sometimes are written in the formulas for derivation as something that you should memorize. In my view, you should never memorize something that you can understand. So, what is a square root of x? It is x to the power of 1 over 2. So, I can write it here. Y of x is equal to x to the power of 1 over 2. And now follow the same logic, the same formula we have, this one. Y to the first derivative of y with respect to x will be, well, the power becomes a coefficient, so it's 1 over 2 x to the power of, and here what we have to do is do the 1 over 2 minus 1, right? So we end up with something like 1 over 2 x to the power x to the power of minus 1 over 2. Okay, so this can be actually rewritten in a much easier and cuter way. Let's say, no, fraction. So we have 1 over 2, and then the negative coefficient means that x is supposed to be written in the denominator with a positive exponent, and here we have square root of x. Why? Well, because 1 over 2 power is the same as square root. So this sometimes is considered a formula for the square root. So how to take a derivative of a square root? You're supposed to do this. You can memorize it as a formula if you want, but then what do you do if it is 1 over 3? You have to also change this coefficient. So anyways, I encourage you to just use this formula all the time whenever you can use it, and don't memorize extra stuff. Okay, the derivative of e to the power of x is the most beautiful derivative you can think of. It's gonna be e to the power of x. It's gonna be like that all the time. And then the derivative of natural log. We go back to our formulas, and we have a formula for that. So we have the fraction 1 over x, and then we have sinus x plus 2x to the power of 1 over minus 1 over 6. So here it's gonna be a bit more interesting. Well, already for the sinus we have the formula, so this is just the cosinus. We write it like that. Perfect. And now the derivative of the second part will be 2 times, here let's write it as a fraction so we actually see the correspondence, and it was minus 1 over 6, and then x is now getting a power of minus 1 over 6 minus 1. Okay, that will be equal to what? We keep the our cosine plus minus the fraction will be 1 over 3. What happened? I just did 2 times minus 1 over 6 and I got 1 over 3. And x will have a power of minus, and then I want to write it as a fraction 2, 7 over 6. 7 over 6. Okay, well, this last example, not the last, this example is something important to keep in mind. Most likely you will not have this 6 here, you can have something like alpha, and instead of coefficient 2 in the utility functions and other functions that we use, you'll have, I don't know, beta. So you'll have to really know how to simplify it as much as possible to get the example, to get a result that you can work with later. So for now, I'm having numbers for you, so it's easy and you understand better. And then, oh wait, I have a conversation. Will we be using a lot no, never. Forget about them. I just show them to you because it can be used in the business cycles. But you don't have to memorize that. You have to memorize out of this, no, not even this part, as I told you yesterday. So you have to know how to take a derivative of a log, for sure. You have to know how to take a derivative of exponent. You have to know this. Well, there's not so much to know, you know, it's okay. So no sinus, you don't have to know how to take a derivative of a tangent, or, you know, all that. Cool. So the last one is here I want to rewrite it again in a better form. So before I write the thing, I'm going to do this. Y equals to 2 times x to the power of minus 2. Okay, now I know how to work with it. This is just a coefficient, so this will work like this. And then x to the power, I know how x to the power works. That is 2 times minus 2 times, here I prefer using times, x to the power of minus 2 and again minus 1. So dun dun dun, we get something like minus 4x to the power of minus 3. And if we want to write it as a fraction, we do. If we don't want to write it as a fraction, we don't. Okay, perfect. So you're gonna have this. If right now you didn't understand something, that is a real issue. because, well, the minimum is okay. You're gonna see it over and over, but this, everybody will assume that you know this. So that derivatives, again, the most important topic of our course for now, for sure. So let's move. I really wanted to explain everything to you without asking, so you don't see that maybe some other people know something better or you don't understand. So this is just something that everybody should understand, and I was expecting, if I asked you to write it in a conversation, I would have to expect everybody answering. So you got it. Now let's move to the second part of our warm-up exercises, and this is something where you have to think economically, except for the last part. The last part is not very well, the last question is not very crucial right now, so you don't have to remember it, the definition of the derivative with the limit. You will see it, but again, if you don't want to spend time on that, and if you struggle with just taking the derivatives, don't spend your time on the definition with the limit. If you know, remember, like it, here you go. So okay, cool. I think that the first one was not so difficult, but this is just pure economics, so let's go real quick through that. We have a total cost function. Q in this case is the quantity of whatever we are producing. Okay, so the total cost is equal to this. Why? Just because it's one example. Now we have to write variable cost function. So variable cost is the part of total cost that depends on the quantity produced. So you know that we have fixed costs, something that does not depend on the quantity, as many, imagine we're producing, we're making cookies. We still have to pay rent of our kitchen, whichever amount of cookies we produce. So that will be the fixed cost, right? Does not depend. The variable cost is the part that depends on the quantity. And in here, it was easy to see that what does not depend is 75, and the rest depends because it has Q. So we're gonna just write that real quick. Minus 5Q to the power of 2 plus 12Q. And that's it. Papa. 75 is the fixed cost part. Find the derivative of the variable cost function. I obviously mean the derivative with respect to Q, right? So I want to know how variable costs change when I increase my Q by 1. And also, this is going to be a function. It's not going to be a constant number because it depends where we are on our production process. So given we already produced 100 details, maybe now additional detail doesn't require as much as before as to produce, for example, the first detail, right? Okay, so let's take a derivative. It will be 3Q to the power of 2 minus 10Q to the power of 1 plus 12 to the power of 1 is the same as just Q. Okay, perfect. So we have a function of the variable cost. Now I'm going to ask you to type me the interpretation of what the derivative of variable cost is. Is a slope. As Q rises, variable cost also rises. Well, the slope Yeah, I agree, but that is just applies to any derivative. The derivative is the marginal. Okay, so exactly what we get, like this, we get marginal cost. And why am I asking, like, is something special? I'm asking because you might know the definition of marginal cost in general as the first derivative of the total cost with respect to Q, right? But what I wanted to show you in this example is that it is also the first derivative of variable cost with respect to Q. Why? Because total cost and variable cost just differ by the amount of fixed cost. And whenever we take the derivative of something that is fixed, we automatically always get 0. So that will be a 0 for the 75, so it is the same. Just as a refresher of a mathematical, economical part of the cost. Cool. So the second one was a bit more interesting. Provide a mathematical proof for the general result that, given a linear average curve, the corresponding marginal curve must have the same vertical intercept but will be twice as steep as the average curve. Okay, first of all, what average, what marginal, doesn't matter. We can say, well, for the sake of clarity, let's agree that we're talking about marginal, variable, average costs, right? So let's say we have average cost curve, and then we want to prove that the marginal cost curve must have the same vertical intercept but twice as steep. We could be talking about revenue. That also has to work, and it can be increasing and decreasing. Okay, we have a reply already. So assuming a linear average cost curve, AC, yeah, let's talk about costs, AQ plus B. So that's perfectly correct. Let me write it with the fractions so it is clearer for those of you who didn't get it. So look, let's start. We see we have a linear average cost curve. So our AC that depends on Q will have a linear form, and you know how linear functions look like. Let's call it AQ plus P, right? Whichever coefficients. Yeah, A and B can take any value. Absolutely. So we're taking A and B as letters just because we don't want to stick to any particular example. I could say, let's take a very special case where the average curve function looks like 2q plus 3. I could, but let's stick to letters. Perfect. So then, how do we get the marginal curve? So marginal cost, as we know, and as we already mentioned, wait a second, will be, yeah, did make sense, will be the first derivative of total cost. So total cost is nothing else other than total cost is average cost times quantity. Why? Because how do we get average? We get average by dividing the total by the quantity produced. So to get the other way around total, we have to multiply average by the quantity. So let's substitute this by this expression, and we're gonna get AQ plus B times Q. And what I want to do is to work a little bit more with it. So to open the parenthesis, and we're gonna get AQ squared plus BQ. Right? I just multiplied both by Q. Perfect, amazing. So now I know that this is the form of total cost. And now I can take the derivative of it with respect to Q. And what I get is 2A Q plus B. And if we compare the two, what we started with, this one and this one, we see that, well, what is showing the slope of the curve? As we've seen for the linear functions, the derivative that shows the slope is this part, the coefficient, right? So if we want to know by how much is our average cost increasing, if we increase Q by 1, well, we always have A. So here the slope is A, and here the slope is 2A. That is how we just proved that the corresponding marginal curve must have the same vertical intercept, but it will be twice as steep. What is vertical intercept? Vertical intercept is the point where our graph of the function intercepts the y-axis. And that will be in the point B. Because imagine Q equaling 0, then the value of AC, or the value of the function, will be equaling B. Okay, so maybe now I should have drawn the graph. So if you didn't get this like completely, it's okay. What the main goal was not even vertical intercept. The main goal was to show that the curve will be twice as steep. And that is true for any linear average and marginal stuff. If you have your marginal cost, if you have your average cost linear, you know that you are already able to plot your marginal curve because it is the same intercept with steep twice as big. Okay, so for the last one, give the definition of a derivative using the limit. I'm just going to, I have one conversation. The derivative corresponds to the limit of dy over dx with h. Yeah, well, you need to put h somewhere inside the dy dx. What is h? H is the increase, right? F prime x. That's a good one. So let's write it here. Yeah, we said F. Wait, I want to use the same. So H. Okay, so the derivative of F, the first derivative of F with respect to x, will be equal to a limit. Oh, I think I can do the limit. Limit h tends to 0, fraction of f of x plus h minus f of x over h. If I just give it like that, you are not understanding anything, because what is h? So imagine that we are on a graph and we are at a point, right? So now what we want to do, we want to increase our x by h. So before I was saying, so given our x increases by 1, how will our y increase? So let's imagine now that we're not increasing our x by 1, we're increasing by h. Okay, so that will be the difference, right? So then, perfect. This will be what? You can see that I wrote it as image of x plus h by the function and the image of x by the function. Well, this is also by how much exactly will the function increase given we increase x by h. So this will be the second value of the function after we increase h. So the corresponding value of the function, the value that corresponds to increased x, and this will be the initial one. So technically, I could also write it like no, I don't want. I wanted to write it through x0 and x1, but I need a graph for that, so I'm not gonna do it right now. What about this definition? So with this definition, what we have to understand is, okay, h is an increase in x, and we want to find a limit of it. Is not just this, right? We're not just dividing one by the other. We want to find a limit of it when h tends to 0. So what we want to pretty much see, if I am coming back to this example, so I was in this point, so here it's gonna be like that. Sorry, I need to do it fast. And I'm coming here to this point of the function, right? So let's get rid of this. So I was somewhere here. Wait, sorry, not this one, the dot one. And let's get rid of this. Okay, perfect. So I was in this dot. Let's say this is the first one and this is the second one. And I increased x by h. So this corresponds to h. And then this part corresponds, this part here corresponds to what I wrote in the numerator. So this is numerator, this is denominator, and we divide 2. And now what does it mean that h tends to 0? It means that I'm trying to reduce this interval to like a dot, not even a dot, right? So I kinda end up here. So when I decrease this, well, if this is initial point, then I'm gonna end up like back here. Given I'm trying to decrease this h as much as possible, I'm saying that it tends to 0. And then I'm going to end up with a limit that I will have to calculate from the, wait a second, that I'm trying to calculate of this ratio. And that will give me the value of the derivative at this, well, the expression more of a derivative at this exact point. We're not going to use this definition much. Maybe in the very first micro classes you will see it again, so that's why I'm showing you how it looks, so next time you see it you don't get freaked out. So just get used to it. Just try to understand, maybe read a couple of Google articles of what does it mean. In Duolingo you have, I think, this with a graph, so check that out. And as always, if you don't understand, you can send me an email. I think I've replied all the emails that I received yesterday. Maybe not all that I received today, but I'm getting there. So this will be your definition. Why are we taking limit? Well, just know that we're taking it in order to get the actual slope of this tangent.